Material, tools, machines, and human control are the actors of production today as they were in the past. But today, under the pressure of competition, industrial plants grow more and more sophisticated. More automation, fewer people near the machines. At the same time, because of defects in tools, materials, machines and operating conditions, faults and breakdowns lose companies billions of AQs and an estimated 11% of productivity every year. The more complex the production systems are, the more disastrous can be the consequences of very small faults. Surveys have shown the average rate of unavailability is 11% for a standalone machine, and it could increase up to 40% for interlinked machine systems. Less breakdown, less time spent on maintenance, less idle time and minor stops, less running at reduced speed, less scrap production. That's the only way to remain competitive. This tool is worn, but it's not visible. However, the quality of the workpieces is decreasing. Control cycles can detect such defects, but what about the quality of the pieces produced before detection? Control cycles are not sufficient. Machine builders keep increasing the intrinsic reliability of machines, but unpredictable conditions occur throughout the lifetime of machines, and efforts to increase reliability are not sufficient. Existing detection facilities do help to prevent faults today, but these systems of monitoring and control are not flexible enough and tend to give unreliable detection and poor diagnosis. The main problem is the inability to diagnose the causes of faults quickly. For typical breakdowns, 80% of the downtime is used for diagnosis and only 20% for corrective action. Preventive maintenance bases its effectiveness on the statistical predictability of failures, but the more flexible the systems are, the more complex the statistical models of prediction become. The results may be more machine downtime for maintenance or too many breakdowns. In order to improve this situation, several European partners have joined together to form the Esprit 2349 consortium. In Italy, Mandelli, the manufacturer of machine tools and production systems. In Spain, Iveco Pegaso, heavy vehicle manufacturers, and Icalan, a research center specializing in advanced manufacturing technology. In France, PSA Citroën Peugeot, automobile manufacturers, Adersa, specialists in process control and diagnostic systems, and the Ensam Research Center. In Britain, Stuart Hughes Limited, prime contractor and specialists in machinery diagnosis systems, and Amtree, advanced manufacturing technology. To design and experiment machines able to detect failures and predict breakdowns is the main objective of Esprit Project 2349. Human beings are sensitive to their environment. They can see and hear. They can express themselves, touch and feel. Human beings feel effort, pain. They're able to stop in time and to regulate their effort according to their own ability. Machines cannot do this. They don't detect when they're suffering and don't stop when circumstances would require it. Machines should be designed to feel pain and be capable of reactions as human beings are. Esprit 2349 makes machines able to feel. Various sophisticated sensors are in use. Accelerometers can detect variations in cutting and vibrations in bearings or gears. Hydraulic sensors are used in connection with hydrostatic spindles to measure cutting forces in 3 different directions. The spindle is mounted in a special sleeve with several pressurized oil pockets connected to sensors. For example, this force will create in the opposite pocket an overpressure, which can be measured by the sensor connected to this pocket. Esprit 2349 makes machines able to understand. Several logical components exchange data, parameters and orders via a local network. A cell controller defines the work plan by giving orders to the PLC. A data acquisition and analysis system called DAS is in charge of fault detection, real-time diagnosis and action planning. A cell diagnostic interpreter called CDI is in charge of data interpretation, deep diagnosis fault reporting, and decision-making at cell level. At every moment, the DAS is informed of the operation being performed on the machine it's connected to, and it gets the data about the normal conditions of that operation from the CDI. It receives the signals emitted by the sensors and runs a logical process to detect abnormal conditions, to provide a diagnosis and take immediate action if necessary. Then the DAS reports to the CDI so it can go deeper in symptom analysis and give a more detailed diagnosis and action plan. Esprit 2349 makes machines able to react. Fault detection causes immediate reaction, withdrawing the tool, slowing down the cutting speed, and so on. Deeper fault diagnosis involves a symptom analysis processed by the CDI in cooperation with the operator or cell controller. Decisions can then be taken for tool management, maintenance management, production scheduling, and quality management. Esprit 2349 makes machines able to learn. For each operation to be processed, data are recorded in the CDI. Signature, that is to say the set of parameters defining an operation, and specific predetermined data about the desired status of the operations, couple, speed, vibrations, and so on. Real conditions of processing can be integrated in the database in order to improve the quality of diagnosis and prediction. practical implementation of Esprit 2349 systems is demonstrated at 3 production sites in the automotive industry. In Mulhouse, in France, Peugeot manufactures 1,300 cars per day, mainly 106 and 205 models. This plant has been chosen to evaluate the system on standalone machines. One critical problem to be solved was to prevent breakage of certain complex and expensive tools used in the manufacturing of suspension legs. In Agnières, in France, this factory is producing the main parts of hydraulic circuits installed on Citroën vehicles. The machines involved in the process are grouped. As the workpieces are machined 8 by 8, if a fault occurs, it can cause damage to several pieces at the same time. In Barcelona, in Spain, Iveco Pegaso manufactures most of the mechanical parts for the heavy vehicles they produce, such as rear axles and gearboxes. The point of interest for installing the Esprit 2349 features on that plant is to test the system on an already existing fully integrated flexible cell. The first results are positive. Beside a significant improvement of quality, it's already possible to forecast approximately an 8% reduction of tool consumption, a 50% reduction of pieces to rework, 60% less scrap production, a 30% reduction of maintenance time, and 40% less downtime. One day, all the components of the Esprit 2349 architecture will be integrated in the machines themselves. And those sensitive machines will make it possible to produce more and better.